let's just say math is a in all you can eat buffet of awesome stuff, and I haven't left the restaurant in 7 years. So let's start proving things. Let's actually start proving things. And one last thing. I talked about this last time, but I want to talk about it again. To prove things about an infinite set, or maybe I'll say to prove universal statements, so for all statements, on an infinite domain, let's call it D. How do we normally prove universal statements? With method of exhaustion, right? But that's not going to work here, because method of exhaustion literally goes and checks every single option. But if your domain is infinite, you can't literally go and check every single option. You just don't have the time, right? So we have to get more clever. Instead, so for example, let's say we're trying to prove for all x and d p of x, right? And d is an infinite thing. So instead of using method of exhaustion to prove the statement p of x is true for every x and d you plug in, instead of that, I'm going to write instead again. I know I already said instead, but it makes more sense to me. Instead, prove that the property of x being in D must lead to the property of P of x being true. So by this I mean D is probably not a random set of things. Everything in D probably have something in common, right? There's some properties they share. And so if you're trying to prove something about infinitely many things, instead of using method of exhaustion to check each one, which would be exhausting, instead, all you have to do is show that the property that all the things in D share naturally must lead to the property of P of x being true. Because then if you show the property of something being in D leads to the property of P of x being true, that means that everything in D must satisfy P of x. This is the idea. We're going to do an example right now, which I hope helps you get the hang of it. Okay. It's a claim. Every square of an even number Actually, it's getting a little weirder. Of an odd number is odd. We're actually proving something now, people. This is what it's all about. We got to it. See, I feel like this is how math works. It's like at the beginning of class, we always say we're going to do something interesting today. And then we take you through so much boring crap. By the time you actually get to the interesting part, you forgot it's interesting. This is the interesting part. We're proving something. Okay, about an infinite set. So first of all, let's write it formally. All right? I mean, this is using some street lingo right here. Okay, this is some vernacular. How would you say this in formal math? First of all, is this a universal statement or an existential statement?
Universal.
Universal, right? So we're saying for all n, what's our domain?
Odd numbers.
Sure. In the odd numbers, which you could write, by the way, as 2k plus 1, as all numbers of the form 2k plus 1, such that k is in z, because we know that's what it means to be odd numbers. Other way. What are we saying about all these odd numbers?
This square is odd.
The square is odd. Exactly. And remember, because of how universal quantifiers and conditionals work, another way you can write this is that for all n and z, n odd implies n squared odd. Right, same thing. All right, let's prove something. All right. So once again, this should make sense to us, right? We try thinking, we go, okay, wait. 1 squared, 1 is odd, 1 squared is 1, that's odd. 3 is odd, 3 squared is 9. Yeah, that's odd. 5 is odd, 5 squared is 25 is odd. It seems that every odd squared is going to be odd, but why? Right? How would you prove it? How would you prove that's always true? Well, how about this? Here's what I'm going to say. Let's start with this. Let's start with an arbitrary odd number, and then prove that that must be odd. Here's what I mean. Let n be an arbitrary but particular odd number. All this means, all this arbitrary but particular odd number business, all this means is that we don't know which odd number it is. Like, I'm not saying n equals 7. I'm not saying n equals 17 or n equals 35, right? I'm just saying we know n is odd. N is a number with the property of being odd, right? But it is a particular number. We can't just keep switching around and being like, okay, let's make n equal 3 now, let's make n equal 5. It is a, like n right now is one number that is odd. We just don't know what number it is. We have to work with that. Cool. So what do we know about n if it's an odd number? We only know really one thing about it. What's our definition of odd?
If it's a multiple of 2 plus 1?
It's a multiple of 2 plus 1. You can write it like 2k plus 1. So I'll say, by definition of odd, there exists a k in the integers such that n equals 2k plus 1. That's just by definition of odd. It means we can find this k. Right? Now I'm going to say, let's consider n squared. N squared equals 2k plus 1 squared by substitution, right? We're just substituting 2k plus 1 into here. And then 2k plus 1 squared, that equals 2k plus 1 plus 2k plus 1 by definition of exponentiation. And then what can we do with this?
Expand or distribute.
Yeah, we can distribute FOIL that whole thing. This is going to be 4k squared. We multiply that, and then you're going to have, what's that? 2k plus 2k plus 1 by distribution, right? Which is 4 squared plus 4k plus 1 by addition. Does this number look odd to anybody? What's it mean to be odd? It means that you're a multiple of 2 plus 1. Well, heck, this is something plus 1. Is this a multiple of 2? So plus 1 does not necessarily mean odd, right? For example, 6 equals 5 plus 1, but 6 is not odd, right? Even plus 1. It has to be an even plus 1. And even is just a multiple of 2. Does this look like a multiple of 2? Hell yeah, right? This can be written 2 times 2k squared plus 2k plus 1 by factoring, right? Does this make sense? And what is 2k squared plus 2k? Well, remember, k is an integer, right? And 2 is an integer. Meaning, since the integers are closed under multiplication and closed under addition, this whole thing right here is another integer. So this can be written as 2 times some integer plus 1 by factoring. Thus, or say note, since 2 and k are integers, and the integers are closed under addition and multiplication, right? 2k squared plus 2k is in Z. So we're being closed under multiplication addition. That just means any two integers you multiply and any two integers you add are going to also be integers in the result. And so the result of k squared is going to be integer. The result of 2 times k squared is an integer. The result of 2k is an integer. And so the result of 2k squared plus 2k is an integer. Thus, since n squared equals 2 times 2k squared plus 2k plus 1, and 2k squared plus, I'm sorry, we don't want that. It's this parentheses then plus 1. And 2k squared plus 2 is an integer. N squared is odd by definition. Can someone put words in my mouth while I'll mouth them and you talk? Okay, no, isn't it? This is amazing. I'll do it, right? I'll raise my hand. This is amazing, right? We just proved beyond any doubt that every square of an odd number is odd. This did not require any assumption, right? This didn't require us to go to check all the infinitely many odd numbers, which, by the way, 2C on written assignment 5 might have given you guys some trouble. And 2C on written assignment 5 said that 2 to the m minus 1 is prime. And it wanted you to prove it or disprove it. Right? This might give you guys, or where n is prime. This might be giving you guys some trouble because if you check the first few primes, 2 cubed minus 1 is prime. 2 to the 5th minus 1 is prime. 2 to the 7th minus 1 is prime. It takes until you get to 2 to the 11th minus 1 to get that it's prime. The point is, if you just check 3 examples, you'll get the wrong idea. That's not true. And in fact, there's some mathematical things that will actually hold and look like they're true until you get to like a millionth example, right? The point is infinity is a lot bigger than 5. Infinity is a lot bigger than a million. It's a lot bigger than a billion, right? It's impossible for us to check if infinite things work. We have to be more clever. And this is the more clever way. I mean, right here, all we did is we said that the property, right, of a number being even is that it can be written 2k plus 1 for some integer k. And then once you have that, right, the property of a number looking like this is that you can square it and it'll look like this, which has the property of being 2 to the integer plus 1. The point is the property of a number being odd naturally leads to the property that that number squared is also odd, right? And since this works for any old arbitrary n, this works for every odd number. So all odd numbers have the property that they're squared, they're odd. Any questions? Does this make sense? Really? Good. If this makes sense, the rest of the class will be a breeze. Because this is the main idea. Everything comes back to this. Okay, well, that's class. Don't have any questions. Game over, people. Or day over. The game is still very much afoot. And we'll continue it tomorrow. Good, good, good. This is good. Good, this all makes sense. And notice, by the way, all this detail that I'm using is necessary to get full credit on homeworks and tests. Yeah. I have nothing else to say. I'm excited. Good, good, good. All right, now that we have the background information and all that out of the way, next class, and from now on, it's just going to be basically proof after proof after proof after proof. And proving a bunch of stuff, proving things true, proving things false.
All right.
Okay.
That's all.
Yeah.
Bye.
Are you saying bye?
Yeah.
Thanks, everyone. Thanks for coming. Alfred, thanks for coming.
Professor, I have a question.
Yeah.
I think you can hit the, like, stop recording. It's
Oh,
just
yeah,
related to homework.